Welcome back to the Deep Dive. If you look at Southeast Asia and the Pacific Rim, you are looking at a region facing an almost insurmountable energy challenge.
Right. You've got this massive growth in electricity demand. We're talking 3 or 4 times 2013 levels by 2040.
And at the same time, they have to hit zero carbon targets. It's not just one country, it's this mosaic of island nations, huge economies like Australia, booming populations.
Trying to square that circle, it really does sound impossible.
Okay, let's unpack this. We are diving into a specialized piece of analysis that proposes a surprisingly cost-effective solution. It's a paper titled, "A Cost-Optimized, Fully Sustainable Power System for Southeast Asia and the Pacific Rim."
And it's really crucial context for you, the listener, to understand the timeline here. This is an older paper. It was published back in 2017.
Exactly, so it's not a forecast.
No, not at all. It's what's called an overnight cost optimal system simulation, and it was designed for a hypothetical target year of 2030. The whole purpose was just to investigate the case in principle.
Could a 100% renewable energy system even be technically and economically viable for a region this vast?
That's the core question.
So our mission today is to discover how the optimization model made that future not just achievable, but astonishingly cheap, and what surprising trade-offs popped up along the way.
To do that, the researchers used linear optimization over a full year with an hourly resolution across 15 different subregions.
So every hour of the year.
Every single hour, they threw in all the renewable potential, solar, wind, geothermal, you name it, and just asked the system to minimize the total annual cost while meeting all that projected 2030 demand.
And as we said, the region is just massive.
Oh, huge. Everything from developed economies like Australia and New Zealand to these really fast-developing nations like Indonesia, Vietnam, and the Philippines.
Okay, so to test the big ideas, they modeled 3 key scenarios that we really need to focus on today.
Exactly. It all came down to how the energy flowed.
Yeah.
First, you had region-wide.
The totally decentralized one.
Yep. The 15 sub-regions were basically treated as isolated islands. No connections.
And scenario 2.
That was area-wide. This was the other extreme, completely centralized. Full interconnection across countries using high-voltage direct current lines.
The big ASEAN supergrid concept we hear so much about.
That's the one. And then the third scenario was called integrated.
And what did that add?
It took that area-wide supergrid and added this massive operational shift, integrating flexible demand from 2 new sectors, industrial gas synthesis and desalinated water production.
Okay, let's start with that classic engineering approach,
Right.
connecting everything up. I mean, we always assume that more connection means more savings, right? You ship cheap solar power from a sunny place to a cloudy one.
That's the theory.
So comparing the fully decentralized scenario to the centralized area-wide one, what was the actual saving from just building those HVDC connections?
It definitely helped. It confirmed the basic idea. In that decentralized scenario, the levelized cost of electricity, the LCOE.
The average cost to produce the power.
Right. It came out to 66.7 euro MWHs.
Okay.
When they switched on the centralized area-wide grid, that LCOE dropped to 63.5 euro RLH.
So that's a solid 4.5% decrease.
A 4.5% decrease in the total system cost. Yeah, it's significant.
I have to say, that's a bit counterintuitive to me. Building a massive transnational HVDC grid is wildly expensive.
Yeah.
How did the model find that it was more competitive than, say, just building more local batteries to handle daily fluctuations?
And that's the key. It wasn't about displacing daily storage like batteries. It was about managing seasonal and regional differences.
Okay.
The grid lets you leverage these wildly different weather patterns and demand profiles. If it's peak summer demand with low sun in one area, they can pull power from a cooler region that's having a high wind day.
So the grid reduces the need for expensive seasonal storage, not daily storage.
Exactly. It balances those big regional supply differences.
But this is where the study gave us a really interesting surprise, right? It found a pretty hard limit to that supergrid idea.
It did. And this is critical for you to understand if you're following the energy transition in Asia. The model's findings really contradict that dream of an Asia-Pacific supergrid that so many people have promoted.
What do you mean?
The model showed that exporting low-cost renewable energy from really distant regions, specifically from Australia up to high-demand centers like Indonesia or Vietnam, was simply not cost-effective.
Wait, why not?
The cost. The cost of the HVDC lines needed to bridge those multi-thousand-kilometer distances, particularly the submerged ocean cables. It just outweighed the cost of building local storage in the places that needed the power.
Wow. So local storage technologies were actually more competitive than those massive transmission lines.
They were. So while connection helped, locally and regionally, the idea of this massive cross-ocean energy transfer was economically dismissed by the model.
That really flips the script.
Yep.
Distance storage beats distance transfer. So if these huge transnational cables weren't the real game changer, where did the model find the real efficiency gain? It had to come from that final scenario.
Absolutely. The real aha moment comes from scenario 4, the integrated scenario. This is where the system stops just serving fixed electrical demand and starts treating industrial processes like flexible energy sponges.
So what happens when we add in the flexible demands of seawater reverse osmosis desalination and industrial synthetic natural gas generation?
The cost just drops off a cliff. The integrated scenario drove the total LCOE down to just 51.1 euro MNWH.
51.1.
Yeah. And let's put that in context. Compared to the first decentralized system at 66.7, that is a jaw-dropping 23.4% decrease in the entire cost of the power system.
You have to understand the scale of that. I mean, they've cut nearly a quarter of the total system cost just by changing how they define and use surplus renewable electricity. But how? How does producing gas and water save us money on electricity?
It provides extreme flexibility. Think of SNG synthesis, that's power to gas, or PTG like a giant flexible sponge. When the sun is shining too brightly and the wind is spiking, instead of having to curtail all that cheap power, the system just instantly directs it to facilities to make SNG or desalinate water.
And those industrial processes don't need to run all the time.
Exactly. They can run only when electricity is cheap and abundant. And this capability, it reduces the pressure on traditional expensive storage like batteries by a whopping 48.5%.
So you just don't need to build as many.
You don't need nearly as many batteries or pumped hydro dams because this flexible load is just soaking up all the oversupply.
It's such an elegant solution.
It is. The overall economic benefit from integrating those two sectors was about 9.5% in relative terms for the annual system cost.
So the goal isn't just generating electricity anymore. It's maximizing the use of renewable electrons for whatever the most valuable output is in that specific hour. Let's dig into what technologies actually, filled up this new cost-optimized system for 2030.
For Southeast Asia, the model was incredibly clear. Solar PV was the undisputed least-cost renewable energy source, with wind coming in as a close second. Solar is just dominant in that part of the world.
And how is that solar capacity broken down?
In the centralized scenario, the PV capacity was split. About 2/3 was utility-scale PV using single-axis tracking.
The panels that follow the sun.
Right. And the remaining 1/3 was dedicated to PV self-consumption.
And we often focus on those huge utility-scale plants, but that prosumer power, the self-consumption from homes and businesses, that played a huge role too, right?
Absolutely vital. That local rooftop PV capacity reduced the overall peak load of the entire centralized system by 5.4%.
That's a huge number for a whole system.
It is, because even if installing panels on your roof is a bit more expensive per watt than a desert solar farm, the benefit of shaving the system's overall peak demand hours, especially on hot afternoons, makes it an essential cost-cutting strategy.
And speaking of peaks, how did the system actually manage the intermittency? How did it keep the lights on 247 in a 100% renewable world? What was the storage hierarchy?
It has to be tiered based on duration. So for daily needs, you have batteries. They have fast response times but limited duration, so they were mostly used on a daily cycle.
Charging when the sun is high, discharging at night.
Exactly. Pumped hydro storage operated in a very similar way.
Okay, what about for longer periods? A few cloudy days in a row.
For those midterm needs, the model used adiabatic compressed air energy storage, or ACS. That's basically storing energy by compressing air into huge caverns.
Right.
But its use actually dropped significantly by almost 74% as the grid got more centralized.
Why?
It confirms what we said earlier. Trading electricity between regions was often more economical for bridging those multi-day gaps than building a specific local midterm storage technology like ACS.
So the grid is great for balancing those mid-range fluctuations, just not the super long-distance transfers. That makes a lot of sense.
Precisely. And then finally, for seasonal storage, the long-duration fuel came from the synthetic natural gas created through power to gas.
The flexible demand we talked about.
Yes. And that gas storage was discharged mainly during the summer months to offset the huge peak loads from air conditioning in the hot, humid ASEAN region. It's the ultimate example of using flexible industry to solve the toughest energy problem of all: seasonal balancing.
So let's tie this all together. The numbers from this 2017 analysis point to a technically feasible and really cost-competitive path forward for 2030. But let's connect this to the bigger picture.
When you look at the competitiveness of that final system, it's pretty astonishing. This study's finding of an LCOE range of 5166 euro in WH for a fully sustainable system. I mean, that's highly competitive even by today's standards.
And that's the thing we have to remember. This study was published in 2017. If their model showed a 100% renewable system costing 51 euros per megawatt hour based on their 2030 cost assumptions from back then, what does that tell us about the system today, given how drastically the cost of PV and batteries has plummeted since 2017?
It tells us the core argument is exponentially stronger now. And when you compare that 51 euro LCOE to the non-renewable alternatives, the economic case just becomes undeniable.
What were the assumed costs for those other options in the model?
Nuclear energy, for instance, was assumed to have an LCOE of 112 euro milliwatt,
Double the cost.
more than double. And coal with carbon capture and storage, or CCS, was projected at 126 euro LOW.
That is a staggering difference. This isn't just an abstract number. This means every time a country in that region considers a new fossil fuel or nuclear plant, this model suggests they could potentially build a 100% renewable system for, what, less than half the price?
That is the powerful final implication. Based on the relatively conservative cost assumptions used for 2030 in this study, a 100% renewable system is shown to be fundamentally more cost competitive than high-risk alternatives like nuclear or CCS.
And that's before you even factor in all the societal and environmental costs.
Exactly, before health risks from emissions or nuclear waste disposal even enter the conversation.
That's a powerful way to wrap this up. This 2017 analysis gave us a fantastic look into how the Southeast Asia and Pacific Rim region could achieve energy independence by 2030. They did it by prioritizing cost-effective solar PV, building smart but limited regional grids, and crucially, treating water and gas production as highly flexible energy demands.
Yeah.
So the big thought for you to hold on to here is the value of flexibility. That massive cost drop, that 23% reduction, it didn't come from some miracle technology. It came from recognizing that controlling demand is far cheaper than building expensive storage to meet fixed demand.
And this raises one final important question that the study flagged for future research. The integrated scenario, it generates a substantial amount of excess heat as a byproduct of SNG synthesis and biomass plants.
Right, waste heat.
Exactly. And while the study suggests this usable heat could cover some industrial and residential heating demand, the model didn't actually quantify the full economic impact of using that heat.
So it could be even cheaper.
It could be. More research is needed to see how capturing that wasted heat could drive system costs down even further.
A compelling economic rabbit hole to end on. You've just gotten the shortcut to being well-informed on a cost-optimized, fully sustainable power system for Southeast Asia and the Pacific Rim. We'll see you on the next deep dive.